Okay, I have some helpers here today for my joke of the day. This is my niece Elsie, and she has a joke. Go ahead.
What does a crocodile say to a crocodile?
What?
Crocodile!
And my nephew David has a joke. Go ahead.
What did the mama corn say to the dada corn?
What?
Where is popcorn?
Nice. And do you have one, Adam?
Yeah.
Go ahead.
Allie's ready.
Okay, well, thank you for the jokes. Let's get into the lesson for today. Kids, you gotta love them. Well, I'll tell you what else I love, and that's integrals. I'm looking at a new packet. Integration by parts is the heading, and you might be thinking to yourself, wow, I've really kind of enjoyed integrals. I've really enjoyed working them over the past few weeks or so, but I feel like I'm sold short. I feel like I've got techniques. If you look around this warm-up, one would be almost too quick for us. We've got trig rules that can help us with 2. We've even got U substitution that can help us with 3 and 4, but I've sold you kind of short for examples like 5 or 6. Just to walk down memory lane, let's look at a couple of these. If I were looking at number 1, and feel free to try these on your own and just check back in with me, or just join me on the review. I don't think we'd hit any trouble. We've got a rule for all of these until we get to this term here. You might want to rewrite that as x to the 1/2. And then I think everything's set up for you to take an indefinite integral here. You've got integral of 5x to the 9th, so 5 over 10, 1/2, x to the 10th. Then we change this to that format, x to the 1/2 power, to know that it goes up a power to 3/2. And we divide by 3/2, so I'll multiply by its reciprocal out front. What's the integral of 7? So 7 and tag on the variable. And then the special rule. This is good review too, right? What function, we'll leave the 2, but what function has 1 over x as its derivative? And that's the natural log. So we always wrote this as the ln of the absolute value of x. And don't forget the plus c, right? I don't see any limits of integration at the top or bottom of that integral sign, so that one looks good. For 2, right, I'd have to brush up on my trig anti-derivatives. You got to think, you know that the 3 stays, but you got to think of a function that has negative cosecant cotangent as its derivative. That would be the integral of this. And checking back up on that, I get cosecant. If I were to derive cosecant, I would get this back. So if I'm going to integrate this original, I get this as a solution with a plus c. Okay, so a little bit of trig. Then we got into, this is still a walk down memory lane, but we got into questions like 3 or 4 where we said, oh, okay, well, this is a product. I didn't say we couldn't integrate any product. We have some inside and outside action going on, and we would let u equal the innermost part of the function. And didn't we say usually the more complicated or the higher degree part of the function? So x to the 4th plus 1 was always a good choice. And we use a little integration by substitution here. This is good to brush up on because we're going to do a little bit of this today too with the new method that we go into. So keep this side work in mind. We take a derivative, du dx, of 4x to the 3rd. And then we always, just to be really thorough about it, got dx by itself. So you can just do a quick, easy plug-in. And this will be helpful, and that'll be helpful. So we took it back in our substitution days. We took it back to the original, plugged in as much as we could in terms of u. So x to the 3rd square root of u, and then I'll write du over 4x to the 3rd. And this is the part where I was really happy because you get rid of, I guess I can cross out the x cubes in the problem, and you can write this, keep the integral sign there, but you have that coefficient of 1/4, so 1/4 u to the 1/2 is another way to write it, du, right, instead of saying square root of u. So we did this in the correct order. We integrated and then we subbed back in. So we can integrate now 1/4 times 2/3 u to the 3/2. I'll put the plus c there now so I don't forget it in the next step, but now we can simplify and plug back in. So 1/4 times 2/3, you have 1/6. Instead of writing u, we can write what u equals, x to the 4th plus 1 to the 3/2 plus c. And something I've been neglecting to say that we are going to bring up today too is that all these answers are checkable. We can take the derivative of this by a chain rule and see that we get the original back, and that should work out. 4 was a great one. 4 was a classic. One more walk down memory lane before we get to the brand new stuff. What was it? I think 4 can be done by U substitution, but I don't like having the 3 levels to it. I don't like having the divided by x, the x squared, and the ln. So keep in mind that you can always go back with some of these examples and use pre-calc rules. There was a rule that said that if you had a log of anything to a power, you can swing that power algebraically down front and write this as 2 times the ln of x over x dx. And we had seen problems similar to this, and you have to make your u choice. And I can think of 2 things I would make u. I never make u the constant. I wouldn't really make it just x. There's a couple reasons why we want to let u equal ln of x. Number 1, it's more complicated than x. Number 2, its derivative appears. Its derivative is 1 over x, and that's another part of the problem. So side work, speaking of its derivative, du dx equals 1 over x. Kind of cross-multiplied to solve there. Dx equals x du. Okay, so we'll use this, and we'll use that, and go work some magic. Back in the original, you've got 2. Instead of ln of x, we can write u over x. And instead of writing dx, we can write x du. And that is the happy part, right? As soon as in u substitution we found some special way to get the x's to go away, you're left with a simple expression in terms of u that won't be a pain in the neck to integrate. So integrate this, you get 2 over 2, so 1u squared plus c. And last step is to sub back in. This time parentheses are necessary. In the original, the only thing being squared was really the x. That's why we're allowed to swing the power down. In this final answer, you need the parentheses to signify that you're squaring the whole thing. So I'm proud of us. We've gotten through a lot, but I'm still not satisfied. At the very end here, I want a way to be able, I'll just put question marks by them for now, but I want a way to be able to really go in and confidently integrate something like 5 or 6. 5 and 6. 5 kind of looks like the last one, but a u sub's not going to help us that much. I could try u equals ln of x here, and then do that side work to get dx equals x du. But it just doesn't take me very far. I get x times u times x du. I'm not so happy like I was before when I got those x's to cancel. So just the way that it looks, u sub wasn't helpful. Same thing here. I might let u equal e to the x, but I don't think that's going to make something cancel with the sine of x. And I could let u equal sine of x, but I don't think that's going to make something cancel with e to the x. So bottom line is we need something new. It's called integration by parts. It comes from the product rule. Instead of proving it right now, I want to give you the formula. It comes from, remember way back when we were taking derivatives and we got product and quotient rules? It was like, here's the notation. You're taking the derivative with respect to x of the product of the expression u times v, and it was what? We just took the derivative of the first part times the second part normal. I think we used f and g instead of u and v in our notes. And then we did the reverse, right? We did normal first part times second part's derivative, dot, dot, dot. Well, if I were to integrate all these 3 parts and do a little bit of rearranging, I would get this special rule called the integration by parts rule. And that's what we'll use for the next couple examples. Eventually, I want to get back to being able to solve problems like 5 or 6 on this page. So here's what's important. Let's go to the next page. Can you copy down what you get here? It's going to have a bunch of u's and v's in it. So it's the integral of u dv. And what I mean is the integral of the expression in terms of u with respect to the variable v. So you look at something like what we're going to see in a second. Here's what it equals. It equals u times v, just regular u, regular v, minus the integral of v du. That's what I want to focus on. Again, this is one of those topics that we have to start really slowly, and it's going to take 2 or 3 days of practice before it'll click in and start to make more logical sense. All right, so we're going to give this a try with the first example I see on the page here and keep all this in mind. And luckily we have some guidelines, a little bit of advice about how you're going to set this up. How are you going to pick? You have these choices to make. We have to let u equal something. I'll put that here under example 1. U equals something, and dv has to equal something else. And there's a couple rules about it. It's not exactly the same as it was choosing u back in u substitution. It also doesn't matter which part of this you choose first, but there is a rule that by the end of all this, choosing what's what, I have to have scooped up every single part of this integrand. I have to have accounted for the x part of it, the e to the x part of it, and also the dx. We'll talk about that too. So maybe we could try picking u first. Let's go to guideline number 2. Try letting u be the portion of the integrand whose derivative is a function simpler than u. So look at these two parts. It's like you have a 50-50 chance for u. It's either going to be x or it's going to be e to the x. Can you figure between x and e to the x, does one of them have a derivative that's simpler than itself? And there is only one answer to that. The answer is x, and here's why. X's derivative, in a second, the side work is that we take a derivative of this. So for the part that you choose to be u, we're going to find a du dx, take a derivative, and we get a function simpler than x. We get the number 1. If we had chosen e to the x for u, it would be an easy derivative. E to the x is its own derivative, but it's not simpler than e to the x. So x was a good choice. Let's look at the dv portion. It says try letting dv, here's another reason we should let dv contain the most complicated portion of the original problem. So the dv has to have the e to the x part with it because it's a bit more complicated of a function than just x is. Another cool thing about picking this for dv is because it needs to fit a basic integration rule. We're going to get to some functions we've never integrated before, but e to the x is a-okay to integrate. We know it's also its own integral. There's one little last part to this. I've accounted for the x, I've accounted for the e to the x, but I forgot to account for the dx. And look at that little note it says. Note that dv always includes the dx of the original integrand. So if you're thinking, where does this dx go on this part or that part? Always include it with the dv for a reason I'm about to show you. So here goes the side work. In a second, we're going to plug in to a recopy of this original integration by parts rule. I'm going to recopy it here. So original integration by parts formula is that the integral, just a recopy, u dv equals uv minus the integral of v du. Okay? And half of this we have already. What we're trying to do is plug into this right-hand side. Half of it we have. We know what u is already, and we know what dv is already, but that's not part of this, right? We're trying to plug into this side of that rule. Well, we know du dx. I had started the side work here. If du over dx equals 1, then du equals dx. So we're going to use u is equal to x. We're going to use in for this du here. This part says we can plug in dx, so that's good to know too. And what do you think we're going to do to this? I don't know what it looks like it's set up for, but this side work has 2 parts. This part is taking a derivative of what you wrote for u to be. This next part of the side work is going to be taking an integral of both sides. We're going to integrate both sides with respect to x. Let me do that in green. I'll just write a new version of it. The integral of dv equals the integral of e to the x dx. So maybe make a note to yourself. You've got 2 portions we've been mentioning of side work. In this portion, you're going to differentiate, take a derivative. In this part, you're going to integrate. Integrate. And that's what I think you all are. I think you guys are integrate. So you're taking an integral of both sides, and don't get concerned with the left side. The left side's always going to be the same thing. This is like saying what's the integral of an empty space, so there's a 1 placeholder there, the integral of the number 1. Well, the integral of 1, that's perfect. That would just be x or whatever the variable might be. And the variable here, it says dv, the variable is going to be v. So when you integrate the left side, you always just get v. What does it equal? Well, it equals something that we should be able to figure out. The integral of e to the x is itself. And it would get a plus c, but can you hold off on that? So for now, just put the e to the x, and we'll remember at the very end of the problem to put a plus c in our solution. Okay, so if you've got track of this, I know it's a little wild now. We've got letters and u's and v's all over the place, but we actually have the pieces to the puzzle that we need to plug into this. So this integral of u dv, which is here is u, x is u, this whole thing is dv, is going to equal, let's plug in one by one. So u is x, v, I got to find it, where is v? V is e to the x minus the integral of v du. So v happens again, integral of e to the x, and in for du, we said we could plug in dx. Almost done. X e to the x stays in your answer, minus e to the x's integral, so e to the x will say plus c. And believe it or not, that's as far as it goes. That's all there is to it. Now, we just found the antiderivative of this original, and all these can be checked. If I were to take the derivative of this answer, it would involve a product rule, and deriving that, you would get the original back. And we'll continue to show this in the coming days. Okay, talk to you soon.